sorry, we're on Zoom today only. Hold on, let me turn this off. Yeah, so sorry, we're on Zoom today only. Both my kids were sick at the same time, and so my wife is traveling. So it's, so I thought this was just the best way. So hopefully, so hopefully next week we'll be back to the regular lecture in the live lecture in the classroom. Okay, but I'm glad everyone could still join me on Zoom, or if you're in the lecture hall, so that's fine as well. You can ask questions in the chat. If I'm not seeing the chat for some reason, it looks like, other than just finishing my thought and something's important, you can speak up quickly and ask it. So Ananya, if there are any questions from the room, you can communicate those as well. Okay, yeah, I spent plenty of time lecturing just over Zoom, so I'm, well accustomed to this, so this sort of, setup. Okay, so today we're going to talk about, how to extend the linear regression, the simple 1- or 2-dimensional case we talked about. So on Tuesday into the higher dimensional setting, and so also into the polynomial setting. Actually, once you get the once you get the high dimensional setting, then the polynomial conversion is, a very simple trick on top of it, right? So the fact we're doing both of these at once, we're still going to go at a fairly gradual pace. And the high dimensional setting, if you kind of survive the linear algebra review, then it'll be a simple twist where we formulate the version we saw on Tuesday into linear algebraic form, and then we just solve it using linear algebra, and we're going to get the solution basically as easy as we got in the so in the case just in 1 dimension. And in fact, it's there's another trick we'll do, so it's going to probably be even easier. Okay, for just we get going, let's look at the so the schedule. Yeah, so homework 2 is, so hopefully everyone, so turn that in. If not, the late deadline is still tonight. After that, we'll start the grading. And we'll try and get those back to you by the end of next week. The first one took a little bit longer than we'd hoped, but we hope generally to get the homework scores back to you by the end of the following week. The homework scores on the first homework were okay. I'd hope they'd be so a little bit higher. Most of the kind of there weren't any kind of glaring common mistakes on a lot of the questions on the first homework, and hopefully the scores are higher on the second homework as well. We will have homework 3 out by Tuesday next week, and then they'll give you a chance to start digging into this a little bit before fall break, and then you have plenty of time to deal with that. So after fall break as well. And as you notice, we'll do some more examples in collab today. So we'll come back to this. So yes, okay. So we're talking about linear regression again. And so just remind you that make sure this is working. Technical difficulties here. This was working right before class, and now my iPad pen is not syncing. Okay. Huh. Let me do something. This might cause a problem for a sec with the screen sharing. See if this will resync. Okay, it's working, but now let me get the screen back. See if this works automatically. So great. So okay. So the input to the problem, remember we wrote this as x, so y, and before we were saying this was a subset of R cross R, where x was real values and y was real values, but really we're going to change this now to x being in RD. So what does this mean? It means that we can think of x, y as a set of, again, x1, so y1, comma, x2, y2, up to xn, so yn. So we have n pairs of these inputs. Each one has a so the explanatory variable, right? Remember, this was explanatory, and then it also has the dependent variable. Okay, but now we're going to now each of these xi's is going to be an RD. Okay, so this is going to be a vector of explanatory variables instead of just kind of one value for explanatory variables, right? So we're going to have kind of more things that can be used to make a prediction on the value y. We're still going to keep the value y as just being a single scalar, or each yi is going to be a single scalar value, right? There are ways you can extend this to predict multiple things at once, but those are so much less common, and we're just gonna, in this course, we're gonna stick to the kind of the very, very common version, which is just you're predicting a single value. Okay, so this picture before, where we had x was in here, and y was was this prediction. Well, now x is going to be in RD. Okay, so this is actually a kind of a d-dimensional space down here. Think of it maybe a two-dimensional space, and for each of the of the data points here, right? If this is xi, it might be xi1. Let me write this a little bit larger. This might be equal to xi1, xi2. So it's got two coordinates now, right? Think of a two-dimensional space down there, and that this green function is now kind of a plane up here, right? So there's some sort of kind of when D is two-dimensional, this is now a two-dimensional plane in the linear case. And for each value of x, it's going to be mapped up to the value on this plane here, right? So this is the kind of like structure we'd like to predict. Okay, so we've got multiple possible values in the that are explanatory, and for each of them we'd like to map them to one value, right? It's going to ultimately give us this one value y. So this would hopefully correspond to yi. This would in fact be our yi hat, right? Because this is the so what the predicted value from the model is. All right, so we need to write this down. So mathematically, what is it that we want out of the model? So the model is now going to be our yi hat, right? Which is this value that we're predicting is going to be some model function. I'm going to write this as a function m now, and it's going to parameterize it by alpha. And I'll explain what alpha is soon. You'll see this soon. And it's going to take in this value xi, right? So it's taking in the value here, xi, which corresponds to the point down here. And it's predicting a value yi, which is here, right? And the model is this the green function, which is doing all the work. It's doing the mapping. Okay. And so but before, when we were dealing with the one-dimensional case, the representative of the function was a line. Now we need to extend this to this multi-dimensional case. Okay, and we're going to write this in terms of these parameters. So alpha here. Okay, so the short thing is alpha. If I just write alpha, it's actually going to be a vector. And so we're going to start with alpha 0 plus j equals 1 up to d of alpha j times xij. Okay, so each xi is a vector. So this is xi1, xi2 up to xid. It's a little confusing now. Now there are two subscripts on the x, right? So it's the first, if I just use one subscript with a lowercase x, that's the whole data point. But then that data point is now, it's a vector in RD, so it has d components to it. So I'll just put the two subscripts so next to each other. Sometimes to make it a little bit more clear, you put a comma in between them. But when writing up, I think I'll just put them next to each other because commas are sometimes hard to distinguish from i's and ones and everything like that. All right, so this is the model. This is a linear model, right? It's alpha 0. This alpha 0 played the role of, so the offset, that b value before in the equation of the line. And now I have different slope values, aj, but that depends on which of the coordinates, the x coordinates I have, correspond with different ways of the slope. So it can be sloping, that green plane can be sloping faster in one direction than it might be in the other, and this linear equation is describing it. I can also write this out kind of without the sum. Good thing about this is x0 plus, alpha 0 plus alpha 1 xi1 plus alpha 2 xi2 plus ... plus alpha d xid, right? And so what's kind of, if you see the structure here, what's neat is that this is actually going to, you can actually convert this into like a dot product. Now there's one trick in doing this, and I could write it as kind of a dot product plus the alpha 0, but I'm going to convert this into a single dot product as follows, where it's going to be alpha. Okay, and now alpha is going to be a vector alpha 0, alpha 1 up to alpha d, which is a vector in our d plus 1. So it's alpha dotted with 1 comma xi, right? So xi was a vector in RD, but I'm going to put a 1 on the front. So now this vector here, this is now a vector in R, this is in our d plus 1 here. Okay, so this is equal to alpha dotted with the vector 1, xi1, xi2, up to xid. Okay, so I've created I've taken x and I've added a 1 in front of it, and now it's a d plus 1 dimensional vector, and the linear model is just going to be a dot product. Okay, I could have done the same thing with the simpler version I looked at on Tuesday, where I turned it into x into, which had 1 value, into a 2-dimensional vector. But that, you know, that's probably more complicated than we need now. But when I had multiple dimensions, I already have multiple dimensions. It's already a vector. I can always add just one more dimension. You know, it's so not that much harder to do. And so if I wanted to go back, I could now say, right, that there was actually a 1 here, right? I could have added kind of this 1 in this spot right here. And now you can kind of see it's a dot product. Remember, the dot product of 2 vectors is just I'm iterating along the coordinates and multiplying the corresponding coordinates and then adding all those terms up. So this is exactly, you know, the dot product. So this dot product is showing up again. So, so great. So, okay. So, so this is the linear model in high dimensions that we want to solve for, right? So we want to find this for given a data point in RD, right? Or a set of data points in RD and a corresponding set of values, find the best model. And again, we're going to want to minimize the sum of squared errors. All right, before we go into this, let's look a little bit at, an example. Okay, so this is an example where the idea is that so like a company, and you would like to monitor a bunch of customers, okay, who are like coming onto your website. And this is kind of what they actually do, right? So they want to predict what is the sale going to be of a customer who comes on the website based on things that you can track. If you are setting up a website, you can track, okay, someone logged on, and you can kind of tell based on browser information how long until they moved off the website, they moved on to something else, right? So the first column here, right, is capturing kind of the time that the customer is standing on this staying on the website in like seconds, right? Let's say this is 200, first customer is 232 seconds, second one is 10 seconds, and so forth. The other thing you can monitor is like, how much are they moving the mouse? If they're not really moving the mouse very much, then they might actually be doing something else, right? So that they might, they open the website and they left it open when they're off doing something else. Hopefully, all of you are paying close attention to this, and maybe you have some websites open in the background. You're probably not so like moving your mouse very much. And so the jiggle is kind of some notion, kind of like in like centimeters, right? How much have you moved your mouse somewhat over the screen? It's a little tricky because the screen sizes vary and so forth, but they've assumed there's some normalized way of how much you've moved the mouse. Moving the mouse is probably a good indication on the website that you're interacting with the website. That's probably kind of positive. So that's the second thing. The first customer here is like, say, moving their mouse 33 centimeters. So maybe that's not a lot. And then the third one is the scroll. How much do you scroll down the website? Now, a lot of websites have like this continuous scroll. The more you're scrolling down, the more you're looking for stuff, right? So maybe this is a positive kind of thing to do as well. Okay, and what you'd like to do is finally predict the sales, right? How much money did the customer spend on the website? And this is supposed to be the number of cents that they spend. So the first customer here, right? So let's look at this first customer. They spent 232 seconds on the website. They jiggled the mouse 33 centimeters, and they scrolled 402 centimeters, and they made a sale of $22 and 1 cent. Okay, and I can record this for a bunch of customers, And then I'd like to kind of understand, okay, what traits are likely to get me to a customer who is likely to spend a lot of money, right? Or if there's some point where I think, okay, at this point, the customer is either going to log off or they're going to spend money, and I'd like to maybe pop up a sale item or so something to kind of say, hey, so don't leave, I can reduce the price a little bit. Or to kind of track how well the website is working. Are the customers interacting with it in some way which is positive? I'd like to understand this relationship. Maybe there's too much jiggle compared to other websites because it's somehow not as easy to navigate. All right, so I want to do this and build a model that takes in these X values and is predicting the amount of sales, right? And so how would I actually do this, right? So this is going to be my column X1. This is an uppercase X, right? If I put an uppercase X1, that might refer to the column, right? This is uppercase X2, uppercase X3, and this is Y. And the first thing I want to do is convert this so every data point, this part here is X1, and this is Y1. But I want to convert it into something so I can just do the dot product. I want to add this all ones column in front here. Right, so I want to put a 1 in front of here, and then I can think of turning this set representation into a big matrix, right? So this 1, X1, X2, X3, this will be a matrix. I'll call this X, so X tilde, right? The input was just the columns 1, 2, and 3, but now I've added one column in front of it. And so now this is a matrix in N. N is, I think, 10 here. There are 10 rows times D plus 1. So this is our 10 times 4. Right, so there are 10 rows and 4 columns here because I've added that first column. So I went from a 3-dimensional to a 4-dimensional problem, but now I don't need to separately solve for an offset parameter. I can treat this as kind of any of the other parameters I'm still solving for. Okay, so this is the setup. Okay, and what I would like to do is to now solve for what is the best model here? Okay, so how do I define what is the best model? Right, I like to define something. So if I have a new customer, I'd like to predict their sales, right, based on this data. Okay, so how do we formulate this problem? Right, so now we're going to think of the input as a matrix X in R N times D, and a corresponding Y in Rn. Okay, these are now, I'll treat X as a matrix. I'll take all those data points and I'll stack them together into this way, turn it into a matrix. And then I would like to solve for this Y, right? And so, okay, so I'm gonna, my goal now is gonna be the sum of squared errors again, and as the input X, Y, and some model M alpha. Okay, and again, I'd like to choose the parameters alpha, which are minimizing the sum of the squared errors here. I can rewrite this again as the sum of I through N times yi minus M alpha of xi squared, right? So the sum of the squared errors, I'm going to look at the model M alpha. on each xi, each row, d-dimensional row, and I'm going to try and predict a value kind of yi hat, right? And how close is that to the true yi? I'm going to take those differences, square them, and I'm going to add all these things up, right? So remember, this is equivalent to sum I equals 1 to n of the, so these residuals squared. Okay, again, we have a picture where this down here is RD. So there's a d-dimensional space down here. This is Y, this is R. I'm going to get this, this linear kind of model here, right? So this will somehow be my model M. Okay, and now for every one of a bunch of these data points, x1 is going to map up to a value here, and this is going to give me a y. If this is, yeah, so this, if that's x1, this will be y1 hat, and there would have been a true y. This would be the value of x1 y1, and so there is a true y1, and the difference, this difference here in between these, the difference in between them is going to be the residual. Okay, so now this is again important that I'm only measuring in the error in the prediction y. I'm not measuring some sort of distance to the kind of hyperplane. I'm measuring the error in this one special coordinate, this y coordinate. And in that space, I'm measuring how much error do I have. And this works the same way we did with a kind of, with the one-dimensional case, but now we have this plane instead of just this line here. Okay, and we can just formulate it again as a, you know, as this, so dot product, right? So this was yi minus alpha, which is everything in my model is controlled by this alpha vector, 1 xi squared, right? So I can, because it's a dot product, that encodes that it's this linear function. And so my model here is going to be this linear plane in this higher dimensional space. For every value, every d-dimensional coordinate of x, it kind of lifts up. You think of it, there's some value y it predicts, and that's a linear relationship between, as I change x, it linearly changes the value y. And so this is giving it as this linear model in this kind of d plus one dimensional space. All right, so I want to minimize the sum of squared errors the same way I was doing before. Okay, and now I need to solve for, you know, I want to find, the goal is to find alpha star, which is going to be the arg min over all alpha and r d plus 1 of the sum of squared errors given the input y and the form of the model that depends on this parameter here, so alpha. Okay, so I want to minimize this, this over alpha. In fact, we might think of writing this as x and y are given and the structure of the model is given. So this is really a function of alpha, right? I can write this, right? So I want to do a star arg min d plus 1. So the minimum d-dimensional vector for this function fs of alpha, the score function, I want to minimize the score or the cost. It's a function of alpha. And so it, you know, so it turns out that a star, I can write down this with the solution with the simple piece of linear algebra. There's a simple both multiplically basically closed form solution. I can just solve this as x tilde. Remember, that's x with the 1 added in front. Transpose x, so tilde. I take the inverse of this. I multiply it by x tilde transpose times y. Okay, so this is the solution. This is kind of important equation. This is something you should try to kind of internalize. Okay, so this is this equation for solving for the least square solution is kind of something you should probably know. And if I ask you to kind of write basically this down on the kind of on a quiz or something, or to like write this down in Python, you should be able to remember this. Okay, this is it's something, you know, you can memorize it. We'll explain it a bit more and see where we get to this, and you'll understand it a bit more. But this is important. This is something you should, you know, try and remember. It's a very important solution, and it automatically gives you the minimizing the solution which minimizes the sum of the squared errors. All right, so let me write this down again on the next slide. Alpha star, right? The optimal choice of alpha is x tilde transpose x tilde inverse x tilde transpose y. Okay, so let's break down what is this actually doing. Okay, so the first thing to remember is that we had this solution in the one-dimensional setting, which was the centered version of x dotted with the dot product with y divided by the norm of x squared, which you could write down as x dot x, right? So this was our solution in the one-dimensional setting. And if you look at this, there's a correspondence here. This x transpose x inverse is like dividing, right? So the inverse, remember, is like multiplying by 1 over that answer, and so it's like dividing by this, right? So the x transpose x inverse is like dividing by x times x, right? And then this part here, x transpose dot y, or times y, is like x so dot y. Remember, when I take kind of stuff represented by the the data is in the rows, and I have a column vector column vector y, and I transpose x, then I multiply it by y. This is, if x was a vector, then this would be a dot product. Okay, so this is kind of the generalization of, the dot product I need here. Another thing useful to do is to check out the kind of what the dimensions of all these things are. Remember, matrix multiplication and inverse only works if the dimensions follow certain properties, right? So x tilde, remember, this is an element in R n by d plus 1, okay? So that means that x transpose times x tilde transpose times x tilde, right? This is going to be an element of, let's see, this is going to be d plus 1 times d plus 1. Okay, so I transpose the first x tilde, and so I swap the n and the d plus 1, and so the n part and the n part of x tildes are multiplying with each other, and I'm left with the d plus 1 parts on the outside here. Okay, so this is good. This means that this is square, is a square matrix. Okay, it's d plus 1 times d plus 1. So it is feasible I could take the inverse, right? In order to take an inverse of a matrix, it has to be so square. Okay. It also has to be so full rank. Okay. Is this going to be so full rank? So, okay, so this is not totally clear. It might not be full rank. Usually we have n much bigger than d. Okay, so usually we have many, you'd usually want to do regression when you have many more observations than you have dimensions. Okay, if you have many more observations, then you have dimensions, and they might be captured with a little bit of noise. Then it's full rank if the rank is at least so d plus 1, right, of this square matrix. And if it has n rows in it, each one might be generating something that's linearly independent. It's pretty likely to be full rank in this case. Okay, it's not guaranteed to be full rank, and this can sometimes cause problems. And if you take like the data mining course, or you look a little bit later in the book in this chapter and stuff we won't cover, you can do something called ridge regression as well, which will do a small modification to this so that it ensures that it's going to be so full rank, so I can take the inverse. Sometimes if you don't have a something that's full rank, you can take pseudo inverse instead. There's something called the pseudo inverse, and we aren't going to really talk about this in class. If you call one of the built-in functions in Python and it's not full rank, it might call the pseudo inverse instead of the inverse, and so that's it might be able to deal with this case. That generally means the solution is not stable though. Okay, so if it's not full rank, you may not want to solve for generic linear regression. You may need to use this ridge regression technique, or this lasso, this other technique you can read about that will make it so like more robust. Okay, but we're generally gonna, if n is big enough, we should mostly be able to assume that's full rank, so we can take the inverse. Okay. Okay, so and we take the inverse, it's still a d plus 1 by d plus 1 matrix, right? So if I look at x tilde tau x tilde inverse, this is also in our d plus 1 times d plus 1. Okay, and now I can multiply by x tilde transpose, which is going to be, remember, x tilde transpose is also going to be d plus 1 times n, because the transpose reverses the order. So now I can multiply it by this fine. And then y is going to be in Rn, so I can multiply that as well. So okay, so the kind of the coefficients all so make sense in here. Why is this the yeah? So I want to say one more thing. In a lot of cases here, it's easier. Kind of as input to say that x is equal to 1x1, 1x2, 1x3 down to 1xn, right? And just treat that x is this n by d plus 1 matrix, or even we would just say this is our n by d, and treat, and then you have each xi is in our d plus 1. This is okay. This would have been a lot cleaner to write on the slides if I didn't have all these, so tildes, right? Having to write and having to say, and if I could have written d instead of d plus 1 all the time. So often you might assume x has this form already. It already has all the ones in front of it. Or you just don't solve for the offset, but typically you should try and solve for the offset. Okay, so it's not much harder to do, but sometimes it's written like this just to make stuff cleaner. And so elsewhere in the lecture and in the notes and the book, we may drop this tilde and the d+1 in order to do this. But I'll try and make that clear if that is the case. Okay, so why is this the right solution? Let's see, I'm a little... wait, add one more page. So yeah, I want to say quickly, why is alpha star equal to x transpose, x transpose x inverse x transpose y? Why is this the optimal solution? I'm just going to very quickly say, and then we're going to kind of there's a lot more details in. Well, so maybe I'll go over this at the end. But the short answer is that you can write down the cost function, take the first derivative through linear algebra, through partial derivatives, and solve for when that's equal to 0, and this is the answer that comes out. Okay, I'm not going to do this now. I want to make sure I get through everything I need to, and then if you have questions after class, I can go through this. But before we go on to polynomial regression, I mean, this is it. This is the whole algorithm for high dimensional linear regression. Let me do an example in Colab just to see how this works. Okay, and we'll see that this is multiple linear regression. This is going to be pretty simple to do. Okay, so I'm going to, again, write this in NumPy and using the linear algebra package. So I loaded those from like ahead of time. Okay, and then I wrote this down, x as now input. I described this as a matrix. So the first row is 1, 32, 33, 232, 33, 402. Right, so that's the first row, and I printed it down below. You can see that's the first row, and I added the ones in here. So this becomes I think a 10 by 4 matrix. Note when I print y, even though y is a column vector, it's printed as a row vector. Again, remember Python decided to always print stuff as row vectors because it's a lot easier to see, even though it needs to be column vector for those equations to to line up. Okay, and now I can compute the answer called alpha. I called it a here. All I do is I write the inverse. That's a function within the linear algebra package of x transpose x times x transpose times y. Okay, I just write this one line here, and it outputs this answer a, which is my coefficients of the model, right? So it's written in scientific notation, but the first coefficient is let's see, is 262 about. So what that would mean basically is if a customer just shows up on the website, right? Remember, this was modeling customer interaction on the website. They just show up. If all the other coefficients were 0, my baseline is I expect them to spend 262 cents, $2.62. So just getting them to show up is worth something. And then the other coefficients describe something about the model. It's common to want to try and make sense of what does this second, what does this coefficient in front of the scroll mean or in front of the time mean by itself. People often do this. I see papers, I've been in discussions where people are trying to make inferences about them. They really need to be interpreted as a group because there's often kind of correlation between the variables, and this does not tell you necessarily about that correlation in here. And it's so you can't interpret these in isolation. You can only interpret them and how well they fit the model, they fit the model data. And that by looking at the sum of squared errors or maybe the root mean squared error, which would give you a better interpretation. Okay, NumPy also has a built-in function here. It's giving me some warning about this function, but you see the first line, it's printed out the same answer here. Okay, this is a linear algebra least squares function. Okay, and it just, this is built in. There are other ways to implement this. It's such a common thing. There are many different implementations of it. In fact, later in the semester after fall break, we'll talk about another way to solve for this. Okay, but it gives the same solution as our kind of straightforward linear algebra using this matrix inverse. Okay, and so then how would we, if we want to evaluate this, right? The power of this is we're going to evaluate how well this model works. It makes predictions. I'm going to take one of the rows, right? I can pull out, this is the third row. I'm indexing starting at 0. So the third row is x3. I can print out x3. I have, the coefficients 1 in front, then I think that's 6,437 seconds on the website, 343 centimeters of jiggle, and 231 centimeters of scrolling. And the prediction is I'm going to spend about $82 on the site if this is the interaction. Right? If you look at what the actual value was, the actual value of y was so $76.50, right? So we're getting somewhat close to that. Okay, great. Okay, so let's go back and talk about, okay, so this was multiple linear regression. This one kind of equation, once you've converted it, added that 1 in front, represented as a matrix and vectors, this one equation gives you the answer. Let's talk about, I don't know. So doing online, do people need, this would be a spot for a short break? Do people need a little bit of a break, or should we, because we're online, you guys have only been, maybe now's a good time to ask questions. If you have any questions about this stuff, and then we'll move on to the polynomial regression. Oh, okay, yeah. So we went from x to x. So tilde, yeah. So I could have easily written kind of y. This is really y is alpha star equal to x tilde x, x tilde inverse x tilde y. I just dropped the tilde because it's kind of messy to write. And if I'm just dropping the tilde, you can kind of just pretend maybe it's there, or maybe I don't solve for alpha 0. I assume that alpha 0 is going to be 0, and then I can just drop it, right? So I'll try and say if this means one thing or the other, but this is just for convenience of notation. Yeah. Great. Okay, so it's, hopefully this was a pretty simple extension of what we did on Tuesday, and we just wrapped it in linear algebra and did most of the same stuff. All right, okay. Let me go on to, on the slide where you have just x, yeah, if xi is in our d plus 1, are you appending 1 to the rows in x to make, okay, yeah, so I'm not really doing any of it. I'm just playing fast and loose with the notation. Okay, I just don't want to always write the tilde. I don't want to always say the tilde. I don't want to always write it. I just want to. So I'm just sometimes for convenience of notation, I will drop it. Okay, that's all that's going on here. So later in class, when we talk about this, we will kind of sometimes not write the tilde just because it's kind of messy to write. Okay. I'll try and be clear. If it's unclear, we'll try and add explanation if it's on like a quiz or something. And we'll try and be loose about if you write it one way or the other, so we pretty much know what you mean. If we want to ask you explicitly that you need to add the ones in front in order to get the offset, you need to add these ones to get the x tilde, then we will be very, very clear about that. But sometimes it's just a pain to write these things, and so that's why we drop it. Can we use the same formula if xi is an R1? Yes, right. So this would work, right? So if x1 through x2 up through xn, these were in just R, right? And so I wrote kind of x tilde 1, right, as 1 comma x1. Now this is in R2, right? And then I can compile together this x tilde matrix, which is all ones in the first column and x1, x2 up to xn. And I still had y still in Rn. Okay, now I can still solve for alpha equals b comma a is still going to be x tilde transpose x tilde inverse x tilde transpose y, right? So this will still work. It will give you the same solution as I solved for on the other way. Yeah, it seemed a little bit kind of, I wanted to save the linear algebra to this lecture, and then once you do this, you might as well be in higher dimensions, but this will give you the same answer. If you play around with the algebra, you should be able to derive one solution from the other one. But it's a little, that doing algebra with linear algebra is sometimes a little bit messy, and we're not going to need to worry about that in the class. Just kind of know that this is kind of this magical solution. Oh, I'm still unclear of why we need the d+1 offset. What would the problem be if we just ran with d? Yeah, okay. So if we just ran with d, okay, so what's going on? So you can think about this in just this one-dimensional sort of setting, right? Let's say that x is in just real numbers, so R1, right? And y is in R. Okay, and now if I want to fit a model, a line, let's say I have a line through here, right? This is y hat equals ax plus b, but now I don't put the 1 in front. That's corresponding with not being able to solve for this value b. Okay, remember this was equivalent to alpha 1, and this was b is alpha 0. So now I don't know how to solve for alpha 0, and so my equation, right, then the equation for y in general, remember it was alpha 0 plus j equals 1 to d of alpha 1 x I j. Right. So alpha j here. Okay. So if I didn't put the 1 in front, and I'm not solving, right? Then I'm not solving for this guy. That means I don't have an offset. That means that this line must go through the origin. That would be y hat equals ax. But I don't have a b. That offset, that b or the alpha 0, tells me how much, if everything else is 0, if all the x values are 0, what is the what is the shift here? So if I don't put that 1 in front, I'm not solving for the offset. I could use that trick I did before and on Tuesday, where I solve for the linear expression, and then I know it has to go through the mean, and then I shift it up to go through the mean. I solve for the offset that way. But as long as you're using your linear algebra and your matrix inverse, you might as well throw the ones in there and you can solve for everything all together. Okay, so hopefully that kind of answers the question. If you don't put the 1 in there, you're not solving for the offset and your equation has to go through 0. Sometimes you might want that to be the case, right? If you have some sort of physical relationship that you know if all the coordinates are 0, the output should be 0. They're like, how long did you run in the race? And you're looking at how many steps did you take? And like how many times did you move your arms on your like Fitbit and stuff, and you want to know how far you went. And if all the steps and the arm movements are 0, the distance should probably be 0 also. So maybe then you don't solve for an offset, right? So that could be some model that you actually enforce here. All right, okay, let's get to polynomial regression here now. Okay, so for polynomial regression, we are going to, oh yeah, so you are allowed to reason about, spend 0 time, they'd spend $0. Yeah, exactly. So you're kind of enforcing that in the model. Okay, so for polynomial regression, we're going to have a similar picture here now. I'm going to talk about just the case where X is in R1 and Y again will be in R, right? So the input here for this is now for polynomial regression. Okay, the input here is now we're going to write it as X, Y again, but this will be in R cross R, right? So this will be equal to the set Xi, Yi, and each of these will be a subset. And we'll have, so each Xi is just a real value and each Yi is just a real value. There are extensions, they're not too hard, they're just a little, we'll see things like this in the classification part of the class where the Xi's might be multidimensional. You can still kind of use a similar trick. But what I want to do now is to find a function that might be curvy, right? So it might be curvy in the space. I still, for every data point, I'm going to map up to a single Y value. So I'm still going to get a Y hat for each Xi. Okay, but I don't want to enforce it's linear. I want to allow it to be a polynomial. And specifically, what we're going to consider is where the equation looks like Y hat is going to be a model, and I'll write this as a, say, a 2-degree polynomial. So this will be, I'll write, say, P equals 2 down here. So as a subscript, so that's a scalar subscript here as a function X. It's now I'm going to force it to have the following form: alpha 0 plus alpha 1x. This was the linear equation. But now we're going to add a 2nd-degree polynomial term, and that means I take the x value and I square it. Okay, I can lead up to a 2-degree polynomial, and I'm going to get alpha 2 as a coefficient of this. This is our polynomial of degree 2 model for what the equation could be. This model is not complicated enough for the green curve I drew over there. It would have to look, so like a parabola. A degree 2 polynomial looks like some form of a parabola. Okay, so it's going to be kind of a, but if I increase the degree, right, in general, so if instead, I should have swapped the green and the orange colors here, right? But if I instead wrote, let me write this over as red. In general, a model of MP of X, I could write as alpha 0 plus alpha 1x plus ... up to alpha p of x to the power p. I can look at all of these different raised up to the pth power. So if I raised up to like the 8th power, maybe I can get something like that red function. Okay, if I raise it to a high enough power, I can get a pretty curvy function here. Okay, and I can, you can also write this again as alpha 0, which is again the offset. What happens if all the coordinates are 0, plus kind of sum of j equals 1 up to p of alpha 1 times x to the power j. Okay, so instead of looking at j coordinates, p, d coordinates, I take one coordinate and I raise it to different powers. And this is the model that we're considering here. And we'd still like to solve. And again, the goal here, is a alpha, now alpha star p, which is going to be a vector in p plus 1 dimensions here. Okay, which is going to be the arg min of the sum of squared errors x, y over the model p here. Okay, so p of alpha. Something like that. Okay, so we're now minimizing, but we've changed the model. Instead of a linear model, we're now looking at the polynomial model, but I can still write this as a trick is I can still write this as a dot product of alpha times this vector 1, x1, x, just x, 1x, x squared up to x to the power p. I can still write the model as a dot product, but it's a dot product after I've turned the single coefficient x into a p plus 1 dimensional coefficient, right? I could also, there's another way you can write this here. This is also equal to, if I start j at 0 up to p, then I just get alpha j x to the power p, because x to the power 0 is going to be is going to be equal.
Yeah. Hey Jeff, so we can't see the bottom part of it because this is covering.
Oh, okay. Yeah, you can probably adjust how you're zoomed in to the slide. It's being shared, but
is it? Yeah, I thought it's just from your end. Let me see.
Yeah, it should be on your end.
Yeah, all good. Thank you.
Okay,
Sorry.
great. Yeah, this happens all the time. So, okay, great. Yeah. So what do these look like, right? So let's go through kind of another example here, and then I'll tell you how to solve it. The solution for it is going to be like maybe you can even kind of already guess based on, okay, it's a dot product to kind of change the x a little bit, but let's go through a little example here. And so I'm going back to the height and the weight here, but what I'm doing instead is I'm just the first top part of the data on the left is exactly the data from the we used on Tuesday, and then I've added some additional data on the below that, because to fit a more complicated model, I actually am going to want more data points for it to make sense. Okay, so I fit some more data onto this, and this is more people with height and weight. Sometimes I have half inches and so forth. And so I've drawn the linear model, but what I'm going to want to do is to find a polynomial model. Let's see. Maybe there's a polynomial model that looks like this. Okay, so this polynomial model is kind of close to the linear model. The linear model doesn't do bad, but maybe I can do better if I allow the curve to be a bit more curvy. And kind of a key thing to kind of keep in mind here is that the error is still measured a different color here. The error is still measured in terms of, so this residual. Okay, this is, this is how I measured the residual for the linear model, right? The distance to the line. When I'm measuring the error on the polynomial model, it's pretty much the same thing. It's the distance from here to the value I would, so predict, right? So this is, say, yi, and this value here, if I zoom in, this value is yi. This value is yi hat. Okay, so let me draw this example here. This height would be yi, and the height on the model, if I were to look at the x value and see what it predicted on the model, this is yi hat, and the residual is still measured exactly in the same way as before. Okay, I'm just measuring the distance in the y thing, and so kind of I can write down the sum of the squared errors of x, y, and some model MP alpha, right? This is again going to be I equals 1 to n of the true yi minus MP alpha of xi squared, right? So this difference, I'm measuring this difference right here. This is exactly, so this residual value, right? It's just measuring in the y coordinate. Okay, so because I've just measured the residual, when I move to a more complicated model, as long as it's a function, I can just measure error in the same way as before. So it kind of extends these pretty smoothly. Okay, let's go see how to do this in Python. What do we have here? Okay, this is another thing linked off the page for today. We're going to do this again. We're going to do plotting in this example, and we're going to see how to get those plots again, but now with polynomial curves. Okay, and I haven't told you, if you look at the second one here, I haven't told you how to solve for it yet. And I'm going to kind of abstract this into a function now. Okay, you're also seeing how to define a function inside of Python. Okay, you do def plot poly, it takes in x, y, and p. In this case, x and y are going to be vectors, or no, are going to be, x and y are going to be these n-dimensional vectors. I don't need to specify n, I just know they're vectors. And p is going to be a scalar, which is the degree of the polynomial. Okay, I'm going to plot a scatter inside of here. So I'm going to call this with data. I'm going to do the plotting like we did on Tuesday, and I'm going to call this polyfit function. Polyfit function I've highlighted there, which is a thing in NumPy we mentioned. But now instead of a linear function, I'm going to allow passing this parameter p, right, which will determine the polynomial. Okay, we'll see how to. We'll go through how to solve it after I go through the demo, and I'll print out the coefficients. And then it's got, the nice thing about this thing is it's got a fit that this f fit function, I pass in the coefficients, and it knows how to, it then gives me this f fit, which allows me to evaluate a point. So a point S. So for any point S, now that's going to be an x value, it'll evaluate the function. This is kind of the built-in command how this works. And I'll draw this now as a line of a red line of width 2. And I'll write the degree, and I'll write down the degree of the fit. Okay, so let's see this on some data. This is now the data I wrote up on the slide, the x and the y, the height and the weight. Okay, and now I can run this with the 4th degree polynomial, and I get the blue data points, and I get the red polynomial curve. Right now, you can see that this fits better than the 1 dimension. I can now, the reason I wrote it as a function is now I can go and and I can change that polynomial, and it reruns it, replots it, resolves for the line. Now it's solved for the best linear fit, right? If I change this to a 2, it gives me a polynomial fit. Okay, this is degree 2. This is a parabola. You can kind of see it's curving a little bit through there, not very much. It's not that far from a linear fit, so I'm going, the best I can do is have a parabola that the bottom of it is very far away, but I do get a little bit of a curve here, and that's it. It decided that was the best solution for this, if a degree 2 polynomial. If I do a degree 3, also it's a pretty good fit, similar to the 4-degree polynomial. Yeah, so if I have a good fit with a degree 3 and I have a good fit with degree 4, you know, what's the right thing to do? That's something we'll talk about next week on Tuesday. How do I decide was a good fit? If I go up to something crazy like 10-degree polynomial, okay, there's a couple things that happen. One, this is actually fitting through the data better. There's still a spot here on the right where it's not quite fitting perfectly. Those two kind of did something weird. If I increase the degree enough and I worry about a matrix inverse problem and some other stuff, then I can get to actually go through those points. But it gave me an error. It says, well, it didn't really give me an error. It gave me more of like a warning. It says polyfit it said it's poorly conditioned. Poorly conditioned means when I tried to take the matrix inverse, it was pretty close to not being so invertible. We'll see the solution involves a matrix inverse again, and the matrix inverse, the matrix I tried to invert it's pretty close to not being invertible, and that meant that I was, it's giving me a warning that something might be going wrong here. If I do, let's see if I do 20 here, what happens? Okay, yeah, it's doing something even stranger here with 20. The polynomial, once I got outside where the data is, it decided, okay, I'm going to do something crazy. But it goes through it's going through the data pretty well. It's not quite going through all the data, and then there's still this one spot where it misses it, and this has to do with it's trying to do something that's not quite in the it's not quite the perfect matrix inverse, because some matrix is not conditioned properly. All right, anyone have any questions about this code? Or about how this works? Again, you'll have access to this. You can go and do this, play with this yourself. This is a pretty kind of simple, pretty straightforward. We'll call just this function, this polyfit function. It'll give the coefficients, which I printed out. And if you pass it into this poly1D function, it will know how to interpret those as another function, which is just going to be the dot product after I do the kind of, as I was showing on the previous slides. Okay, but probably your homework will ask you to do something related to this, so this would be a good thing to make sure you understand. Okay, let's go back and explain how we get the optimal solution for the polynomial, for the polynomial regression. Again, the input is going to be, and I'll just write this as a vector x and y. This would be an r n times rn, right? So it's two n-dimensional vectors. The model m p alpha is going to be is going to take in a scalar x. It's just a real value, and it's going to output j equals 0 up to p, this parameter p of alpha alpha j times x to the power p, right? Remember now alpha equals alpha 0, alpha 1 up to alpha p. Great. So, okay. Okay, this is the model, and we want to find, the goal is to find alpha star, which is going to be the arg min over alpha in rp plus 1 of the sum of the squared errors. Let me write this out explicitly here, of yi minus the model p alpha at xi squared, right? So the same as the sum of squared errors before. Okay, and how we're going to solve this now, we kind of need two steps. We're going to create a matrix x tilde p, okay? This is going to be, okay, for every row, right? I want to write down the model as a dot product. So every row is going to be in n. This is going to be in n by p plus 1. That's kind of interfering with this. This will be n times p plus 1, right? So it's going to have n rows, one row for each of the data points, and p columns. First column is 1, second column is x1, right? Then x1 squared up to x1 to the power p. The second row is 1, x2, x2 squared, x2 to the power p, and then 1, xn, xn squared, xn to the power p. Okay, this we'll call x tilde p, right? This is the first step. I construct this expanded sort of matrix, and the model should be xj. Yes, thank you. This should be x to the power j. Great. Okay, and now the alpha star in this case is just going to be xp tilde transpose xp tilde inverse xp tilde transpose y. Okay, so the solution is exactly the same solution. Basically, what I've done is I've take this one-dimensional data point x, and I've turned it into a p plus one-dimensional sort of data point. Right, so this data point, I'm going to call this, this will be some data point v1, which is going to be an rp plus 1, right? So this data point, this will be v2, which will also be an rp plus 1, right? So I've taken these one-dimensional sort of data points, and I've turned them into high-dimensional data points. Once I have high-dimensional data points, the model, remember the model m kind of p alpha of x I is now going to be equal just the dot product of alpha with vi. So I've turned them into these v vectors in p plus 1 dimensions, and the model is again exactly a dot product, right? Once I've done this kind of lifting, this expansion sort of conversion here, right? And so then once I have them in this form where I have these high dimensional data points and the solution is a linear model, once I've done this nonlinear transformation, then I solve it the same way as I did with the linear models. Okay, and I get exactly the same kind of solution here. Okay, so that's it. Let me just do quickly, I'm running out of time. Well, let me do one very simple example just to make this clear. 2, 4, 3. This is my x and this is my y. 1, 6, 5. Right? I want to expand into x p tilde, and let's do this with p equals to 5. Okay, so the first column is going to be all ones. The second column is just a copy of the X matrix, which is one-dimensional. The third column is that squared, right? Is that entry squared. The fourth column is it cubed, so that would be 864 27, then 16, 256, 81, and then 32, 10, 24, 243. Right? So this is now an element of 3 times 6, right? Okay, so this is how the expansion works. Once I have this x tilde p matrix, I can do the same techniques as the high dimensional linear regression, but I've done all the polynomial part in a pre-processing step, and then the solution is the same after that. So great. So we'll stop here. If you want to have questions, or I can go a little bit more into why that alpha star is why that's the right solution to that. But well, this is that's a little bit extra. You don't need to know that, but if you're curious, I can go through those steps. But first, if there are any questions on the polynomial regression, but the main part of the lecture is over. And thanks for being online if you're not normally online with this. Yeah. Yeah, I think they'll be fine tomorrow, probably.